Fantastic. So today we have exercise 6 of chapter 2 of Enderton's Elements of Set Theory. Almost forgot the name of the textbook. Okay, so it has two parts. Part A, which says for any set, show that for any set A, the union of the power set of A is equal to A. And part B, show that A is a subset of the power set of the union of A, and it asks a follow-up question: under what conditions does equality hold? Let's start by approaching A first, since it seems just a little bit easier. And as usual, we have two sub-goals. We have sub-goal 1, which is to show that the union of the power set of A is a subset of A. And we have sub-goal 2, which is to show that A is a subset, the union of the power set of A. This will establish that they have the same elements and are thus the same sets. Okay, so let's take sub-goal 1 first, which is UPA subset of A. All right, so how do we go about this? It's pretty straightforward. Suppose X is in the union of the power set of A. Then, by definition, there exists some A in the power set of A such that X is in A, right? But it's also important to note that for all A in the power set of A is a subset. Well, little a is a subset of big A. So for all X in little a, X is in big A. And this just tells us straight up that for all X in the power set, in the union of the power set of A, X must be in A as well. Thus, the union of the power set of A must be a subset of A itself. Okay, that was quite nice. It went by pretty quickly. And now we are faced with the converse, which is sub-goal number 2, show that A is a subset of the union of the power set of itself. Okay, now let's suppose that some X is in A. Now recall that the union, I'm going to write it in purple, union of the power set of A is the set defined to be X such that there exists some little a in big A. There exists some little a in the power set of A such that X is in A. Okay. Now, if X satisfies this condition, then X is in the union of the power set of A. And I will just tell you to observe that A is in the power set of A almost by definition, since A is clearly a subset of itself. So, there exists some little a in big A such that X is in little a, namely A equals A itself. Therefore, I can't write capital T's. Therefore, X is in the union of the power set of A, and we conclude that A is a subset of the union of the power set of A. Finally, we get A is equal to the union of the power set of A, as was desired from the get-go. Okay, and now we're going to have to show, well, that was the first part, right? We showed this, and thus these two sets are equal. Now I have to show that A is a subset of the power set of the union of A, and then we're going to have to figure out under what conditions does equality hold. Now I must issue a disclaimer over here. I am making these videos to the best of my ability, and I do not know if my answers are correct. I try to make them as correct as possible, as verifiable as possible. But this might be one of the few exercises where I just don't have the means or the brains to do it. But let's see. So I want to show that A is a subset. You'll see what I'm talking about in a second. Power set of the union of A. Okay, so let's break it down. When we start putting all these operators in front of each other, it starts to get a bit fuzzy what we're trying to show. But let's just start by noting that power set of the union of A is going to be any set, I'm going to call it little a, such that little a is a subset of the union of A. And of course, the union of A is equal to actually, no. I'm sorry about this. I'm going to change this to big X. Sometimes coming up with the variable names helps. Sometimes it makes them more confusing. I try to use variable names that are the least confusing as possible. But okay, I'm digressing. The union of A is going to be any little x such that there exists some little a in A, yes, such that x is in little a. Okay. All right. Cool. And now what we're trying to show is that A is a subset of the power set of the union A. So for all little a in A is in the power set of the union of A. So suppose little a is in big A, right? And now, what are we trying to show? Then, for all little x in big A, well, there clearly exists some little a in big A, such that x is in A, just kind of by definition. And thus, little x must also satisfy that little x is in the union of A. Okay. And now, what this also tells us is that since x in A implies that x is in UA, then little a must be a subset of UA. And thus, little a must be in the power set of the union of A. It's a lot of A's being thrown around. I'm trying to make each inference and each step into one line as much as I can, but I can see how this is confusing. So please leave a comment or something if things are not being clear for you right now. Okay. Okay. And so we've shown that little a is in the power set of the union of A. And since we didn't assume anything about this little a other than the fact that it is in the big A, then for all little a and big A, little a is in the power set, the union of A. So A must be a subset of the power set of the union of A. And that's how I solve this problem. Now there may be better ways, there's probably better ways to solve it, more intuitive ways. And I encourage you to please comment them or something, share them with the rest of the mathematical community if you can. Excuse me. Okay. Now, the second question was, under what conditions does equality hold? Now, what does this mean? Equivalently, what Anderton is asking, sorry, I'm just going to make a new page here. What Anderton is asking is, when is it true that power set of the union of A is a subset of A as well? And let's just break this down. This isn't intuitive. This is actually probably one of the problems that took me the longest to solve. And I don't really remember how I got to this answer beyond just spinning it over in my head for like a week while I was at work or just doing odd things during the day. But I'll try to break it down as much as I can. So, for this to be true, what the hell was that F? For this to be true, we need the following to hold, that for all x in the power set of union of A, actually just to be consistent with the old notation, in the power set of the union of A, little x is in, sorry, big X is in A. Okay, so the power set of the union of A, again, I like reiterating stuff. I know it's redundant, but it helps, such that is big X, such that big X is a subset of the union of A. Okay. And of course, X is a subset of the union of A if for all little x, big X, little x is in the union of A, and little x is in the union of A if there exists some little a, oops, big A, such that little x is in A. Okay, that's a lot. This is the way I try to approach it initially, just logically trying to deduce what conditions, what equality would mean. But I don't think this gets us very far. At least it didn't get me very far. Then what I tried to do was just come up with different examples because at the end of the day, this is set theory and it is helpful to either visualize it or to come up with real sets that, well, real in the sense that like specific instances of sets that might be able to illustrate something. So, one thing that I figured was always a good choice or a good place to start is the empty set. because the empty set is a very small set. In fact, it is the smallest set possible. And it also has a nice property of being a subset of literally every other set in existence. So I tried to do this. Well, what if the power set of the union of A was the empty set, which is not possible because even if the union of A is equal to the empty set, then we have that the power set of the union of A is going to be the set containing the empty set. So I was like, you know what? Fine, sure. What if the power set of the union of A is the empty set? And then this got me thinking, okay, if the power set of the union of A is the set containing the empty set, or rather the bigger claim that if the union of A is the empty set itself, then either A is equal to the empty set or A is equal to the set containing the empty set. All right, now what do each of these imply? Oh, and first of all, why am I making these claims? I think it's important to just highlight that and show what my thinking is behind why, if the union of A is the empty set, then either A is the empty set or A is the set containing the empty set. Okay, if the union of A is equal to the empty set, then for all x, or rather, um, how to put this? Yes, and then for all little a and um, A is equal to the empty set. Because if A is not the empty set, then there exists some x in little a, and thus x is in the union of A, which implies that the union of A is not the empty set, which is a direct contradiction to what we were to our initial assumption. So let's assume that assuming that the union of A is the empty set, then A can only contain the empty set, or it can have no members at all. Right? And I encourage you to try it and prove this yourself, or just leave a comment and I can expand on it. But now, if A is equal to the empty set, then the power set of the union of A, which is equal to the set containing the empty set, is not a subset of A. Why? Because for this to be true, we need x in power set of the union of A to imply that x is in A. But if A is equal to the empty set, then this would require that the empty set is in the empty set, And we know that for all x, for all everything, whatever you can think of, for all x, x is not in the empty set by definition of what the empty set is. So this crosses out this here um, this possibility. So now we can consider what happens when A is the set containing the empty set. Okay. Oops. If A is equal to the set containing the empty set, then the power set of the union of A, which is equal to the set containing the empty set, is a subset of A, clearly. Oh, oh. Well, there's not much more to it than that. They're quite visibly the exact same set. And there we go. So that is one condition under which equality holds. So you can say that at the very least. Equality holds if A is the set containing the empty set. And now this is where the disclaimer kicks in. I think this is the only possibility. But this may not be the case. Now, let's just think about this a little bit. I might have come up with something. Suppose A is not the empty set, and A is not the set containing the empty set. Then there exists some x in A. X is not equal to the empty set. Oh, okay. Um, but if x is not equal to the empty set, then there exists some y such that y is an x. Thus, y is in the union of A, and this means that what? Um, this means that the power set of the union of A is equal to the set containing well, it's going to contain the empty set because it always does, and then the set containing y, and then it also has to contain A itself. And if the power set, the union of A, um, wait, no. Hold on. Um, no, this is not right. Then y is in the union of A. It means the power set of the union of A is equal to what? This is x such that x is a subset of the union of A. Okay, then this would mean that Sorry, let's say that union of A is just equal to the set containing Y. Then the power set of the union of A is equal to the empty set, the set containing Y, which is just equal to the empty set in X. Okay, and this seems to work, right? And just as to be very clear, I am thinking out loud right here, trying to work this out. I do plan on redoing this series after I finish and polish it up, just go through the whole of the book again. But this is a start and hopefully useful not just to myself, but to someone else too, eventually. Okay, I don't see why this would be a contradiction. Okay, but what we can do is say, but this would imply that the empty set is an A. And what would this be? You know what? As I always do, let's try an example. Suppose A is equal to the empty set and X, where X is going to be equal to the set containing whatever the hell Y is. Then the union of A is equal to the set containing Y. Thus the power set, the union of A is equal to the empty set in X, or rather the set containing Y, which is equal to the empty set in X, which is equal to A. Okay, so A is equal to now let's say A is equal to the empty set and the set containing Y, the set containing Z, or rather I'm going to do this. Set containing X, and the set containing y, which is equal to the empty set big X and big Y. Okay. Oh, I have to erase this. Then union of A is equal to X and Y, which implies the power set of the union of A is going to be equal to empty set X, Y, and the set containing both X and Y. Okay, which is not a subset of A. So it seems like we reach our limit after the empty set or a singleton, which is odd. And this is where I am completely out of ideas, and I will just say that power set the union of A is equal to A if A is equal to the set of empty, the set containing the empty set, or A is equal to the set containing the empty set and X is a singleton. That is, X is equal to little x for little x in our universe, and that's it. I think the rest of the video should be pretty solid, but this is just one question that the where when does equality hold is just a question that I still don't feel like I have a satisfactory answer to. Regardless, I hope this was helpful in some way, and I will see you in the next video. Bye bye.